The non-gravitational acceleration measured for 3I/Atlas at its perihelion distance, located 1.36 times farther from the Sun than the average Earth-Sun separation, represents one of the most intriguing pieces of evidence regarding the object's physical behavior as it travels through our solar system. An astronomical unit, commonly abbreviated as O, is roughly 150 million kilometers, meaning that the measured distance of 1.36 O corresponds to approximately 203 million kilometers. At this location, where sunlight is noticeably more intense than in the outer solar system, yet still not overwhelmingly strong, scientists obtained precise data that revealed subtle but meaningful forces acting on the object that cannot be explained purely by gravitational interactions. These non-gravitational accelerations had two clear and distinct components, both of which occurred within the orbital plane of 3I/Atlas, indicating that whatever forces were responsible were acting consistently with the object's direction of travel rather than at some arbitrary or chaotic angle. The first component of the acceleration was radial, meaning that it pushed the object directly away from the Sun. This outward acceleration measured about 135 kilometers per day squared, which is equivalent to approximately 9 times 10 to the minus 7 astronomical units per day squared. Although such a value may appear small at first glance, especially when compared with the immense gravitational pull exerted by the Sun, it is extremely significant for a celestial body of this size, because even a tiny but continuous acceleration can accumulate into a large spatial deviation over weeks or months. The second component was transverse, meaning it acted sideways relative to the Sun object line, pushing 3I/Atlas slightly forward or backward in its orbital motion. This acceleration was measured to be approximately 60 kilometers, or 4 times 10 to the minus 7 per day squared. Together, these two components reveal that forces other than gravity were actively shaping the object's trajectory, subtly modifying its motion as it passed through perihelion, the closest point in its path around the Sun. If 3I/Atlas is a natural object behaving like a comet, then such non-gravitational acceleration could be explained through what physicists call the rocket effect, caused by the ejection of gas from the object's surface. As sunlight warms volatile ices, such as water, carbon monoxide, carbon dioxide, or other frozen compounds, they vaporize and escape into space at high speeds. Every bit of gas emitted carries momentum, and because momentum must be conserved, the object experiences an equal and opposite push, similar to the mechanics of a rocket engine. This process is well understood in the study of comets and has been observed in many icy bodies within the solar system. Therefore, scientists examine whether the measured acceleration from 3I/Atlas can be accounted for by the amount of gas that would need to be released to generate such a push. Using momentum conservation, the relationship between the mass lost through gas ejection and the resulting acceleration becomes clear. If the observed non-gravitational acceleration is indeed due to sublimation-driven outgassing, the object would need to eject mass at a rate sufficient to counterbalance these measured forces. A typical thermal ejection speed for sublimated gases in the inner solar system is on the order of a few hundred meters per second. Based on this, calculations show that 3I/Atlas would lose roughly half of its mass over a timescale comparable to the ejection speed divided by the measured acceleration, which yields an evaporation half-life of about 6 months. This means that if 3I/Atlas continued ejecting material at the same rate observed at perihelion, half of its entire mass would be gone after only half a year. Such a short half-life implies an extraordinarily rapid rate of erosion, far greater than what is typical for standard solar system comets of similar size or structure. Furthermore, when considering the month-long time interval during which 3I/Atlas travels across a spatial distance similar to its perihelion separation from the Sun, about 200 million kilometers, the implications become even more dramatic. If the object indeed experiences a half-life of 6 months, then over the course of a single month it should lose roughly 1/10, or 10%, of its total mass. Losing such a large fraction of material in such a short duration is not something that could happen quietly or invisibly. The evaporation of ices and release of gas on such a massive scale would inevitably produce a very prominent plume or cloud surrounding the object, consisting of gases, vaporized molecules, and fine dust particles dragged along by the escaping materials. This plume would be detectable through a wide range of observational methods, including optical imaging, ultraviolet sensing, spectroscopic techniques, and infrared monitoring. The release of gas would also likely generate a noticeable brightening of the object as sunlight reflects off the expanding material. Because 3I/Atlas is expected to be observed extensively throughout November and December 2025 by ground-based telescopes and major space observatories, such as Hubble and the James Webb Space Telescope, astronomers will have an ideal opportunity to confirm or refute the mass loss hypothesis. If the object truly undergoes the rate of evaporation implied by the measured accelerations, then the widespread plume of gas should be unmistakable. It may appear as an extended comet-like atmosphere, known as a coma, which would enlarge significantly as material continues to sublimate. Depending on the relative abundance of dust mixed with the gas, the plume might either appear bright and reflective or more transparent, but still detectable through narrowband filters sensitive to certain molecular emissions. Instruments capable of analyzing gas spectra could identify water vapor, carbon monoxide, carbon dioxide, or other common cometary species. These chemical signatures, if present in substantial amounts, would strengthen the natural comet hypothesis. Alternatively, a lack of such emissions would challenge the assumption that sublimation is responsible for the acceleration and might instead imply the presence of non-natural forces. The potential non-natural interpretation arises because the measured accelerations do not align perfectly with what is typically expected from cometary activity. While it is true that comets experience non-gravitational forces, the acceleration patterns are usually correlated strongly with the distribution and orientation of outgassing jets on their surfaces. If 3I/Atlas exhibits accelerations that are inconsistent with the expected distribution of sublimation, or if the accelerations persist even when the object is too far from the Sun to sustain significant heating, then scientists must consider alternative explanations. One speculative yet scientifically noteworthy idea is that the object could be propelled by an artificial mechanism, perhaps something resembling an internal engine or energy-emitting system. While this scenario remains highly speculative and far from established, unusual behavior must be analyzed with an open mind. The possibility of artificial or engineered propulsion naturally draws attention because it could create acceleration effects without requiring substantial mass loss, unlike natural sublimation, which must carry away large amounts of material to produce comparable forces. In any case, the upcoming months of observation provide a crucial window for resolving one of the most intriguing scientific mysteries surrounding 3I/Atlas. If the predicted plume of gas and dust is observed, confirming the rapid mass loss, then the natural, sublimation-driven explanation gains considerable support. If, on the other hand, the object remains unusually clean, compact, and lacking in gas emissions, then the nature of its non-gravitational acceleration becomes far more puzzling, warranting deeper investigation into alternative theories, whether exotic natural physics or something more advanced. The behavior of 3I/Atlas thus stands at the intersection of astrophysics, comet science, planetary science, and the study of interstellar phenomena, offering a rare opportunity to learn about the diversity of objects that pass through our solar system.